Thanks for coming for the lecture 8 in mechanical solids. So hopefully you guys have did a good job in the midterm exam. But for the marking, actually not. So for the student come to the lecture, actually they did a good job. But for many students, they get a very, very bad marks in the midterm exam. And even some students ask me the question, hey, why your questions for an exam question, not from tutorial question? I said, of course not from tutorial question. Okay, and that was the point for exams. Okay, so this question is very interesting. Okay, so they cannot ask questions. So all the questions from the tutorial question, from the next examples. That was the point of exams. Okay, so as well for this guy should know these things. So of course, as I announced yesterday, so midterm exam question has been designed. Okay, I've got exam papers. There are 4 sets of exam questions. So of course, highly recommend you guys to sit in the standard exam question. Okay, and also follow my suggestion to you guys. Please practice all the questions from the tutorial and also the practical problems. Okay, you get an idea. Not just the question will be exactly the same. If I change a little bit, the answer will be totally different. Okay, I hope you guys understand these things. Of course, so we'll keep going for our teaching contents for the lecture 8. So in the previous lecture, we have learned the torsion and the bending and also the maximum stress in beams. So actually, we have learned also a lot of things for the shear stress in the earlier lectures. But actually, for the shear stress, as we mentioned, is one of the major issues in any projects. Not because of EAD, not because many projects because broken because of shearing and bending. So as well for this lecture, we are continue to study the shear in the strain beams or members. So of course, in this lecture, we will learn the transverse shear stress, shear in thin wall section, and shear center. Of course, shear center just give you an idea, but I will not give delivery, just give you further instruction. But first thing is for the transverse shear stress and shear in thin wall section. Actually, it's very, very common in industry project. Okay, especially for civil engineering and mechanical engineering. Of course, it's very important. So that's why in this lecture, we'll give you following things. Develop method for finding the transverse shear stress in a beam. Compare the transverse shear stresses with average shear stresses. Discuss the limitation on the use of a transverse shear formula. So of course, this one I'll give you an idea, but actually we'll come to lecture 11. So all will come together because this is a very, very important topic of this in this topic, especially for the mechanical solids. And then shear flow in build-up members. So this one is basically this typical for all the, for example, for all building of these things, that's really the build-up beams. So the average shear stress within thin wall members, just to give a note, and also spacing of a fasteners along the beam's length. So of course, this kind of topic is basic, but actually many questions were combined with composite beams. Okay, that's why we'll first give composite beam first, and then we'll come to these things. Okay, that's why hopefully you can understand these things. So after this lecture, students should be able to understand the definition of a transverse shear stress, determine shear stress in prismatic beams, understand the concept of shear flow. This is very important for you because some in the previous experience, some students in the exam raised their hand. Hey, Lachao, tell me there's something wrong for the exam question, something the unit different. I said no. You must understand the concepts and also the meaning of the shear flow. So of course, I will in the lecture part, I will let you know what's the things there. Okay, and determine the shear flow in build-up beams. Of course, this one is very critical in engineering. Of course, this will definitely will show up in the exam. Okay, and determine the shear flow in thin walled beams. So actually, as what means, so the key things in the industry, how we understand the structure, how we understand the work, how we define this thing, why like this, why like this, why like that. Okay, so that's everything you will come to understand the things. Of course, yeah, so we mentioned in the lecture 2, and of course we'll practice so many questions and the tutorial questions in the tutorial 2 and the lecture 2, and also further on. So we know in general beam support could be have a bird shear stress and bending moment. Of course, these are all internal, okay? So because we can also solve the problem with the internal stress and internal strain. So actually, because of applied loadings, so beams develop in the internal, of course, internal shear stress in the bending moment, and we have learned a lot of things and in lecture 2 and applied a lot of problems. So of course, we should know there's always, we should find the shear stress, bending moment along the components axial, okay, also the distance of the beam along the longitudinal things. Of course, based on these things, we should get the idea. So shear stress is one very, very important thing. But of course, for these things, we are keen to know where's the maximum, because we should for design. So of course, based on this one, we use the method of section. So you guys, you know this, we have a mid-sem exam for method of section. But of course, in the final exam, we still will have a method of section, because the method of section is one of the very fundamental things to do all the things, okay? So of course, we try to find the maximum shear stress, maximum bending moment, of course, from the shear force diagram, bending moment diagram, so we can get this idea, okay? Of course, based on these things, we can get anything of these structures. Let's say that's from this way, as we mentioned in the lecture 2. This is supportive shear stress. So of course, we also learned from previous lecture, so they're supplementary. So from here, this one will go down for the cross section, but also actually parallel for this one will be equal to each other. So that's very complementary. So you use summation m about some point will be 0, summation fx0, summation f5 0, you will get this answer. We did this one before. So from here, we should know for longitudinal and transverse shear stress, they should be equal to each other in amount. Okay? So of course, based on this one, we should know. So that's what for these things, we did everything here. That is the average work. So from here, we work on shear stress from the method of section. But actually, it's from average value. So from here, so we should know that's over the beam. So it's the result of transverse shear stress distribution that acts over the beam's cross section. So that is average, the results. But actually, from different location, they will have different amount of the shear stress. That shear stress is called transverse shear stress. Of course, it's distributed across the whole section. So let's see the cross section like this way. So that's what from here, due to this kind of thing, as we mentioned, for the complementary and also shear stress, then of course we should know the longitudinal and the transverse shear stress are equal in magnitude. And of course, based on this, we should also know idea. In any location, you could have a different shear stress. But you know, for any parts, we saw the on the top, on the bottom, on the edge, there's no shear stress. Can you see any shear stress on the top? No, there's no anything on the top. Okay, so from here, you will see on the top there's no, on the bottom there's no. So that's why from here they should change here. That's why they see something different, not just equally contribute. So that's why we should know how we can work out these things. So actually, we can see from the shear stress what kind of effect will be. So before we can start, we can get an idea. The transverse structures. So actually, so always has its associated longitudinal shear stress acting along the longitudinal plane of the beam, as we mentioned before, because of this. So that's why from here, we cannot say this, but we can see from example in our daily life. For example, here is two type of the board. One, this one for the figure A, these are boards, just smooth boards, and they are one by one, atop of another. So this means they're not bonded, just smoothly they are atop each other. So for this thing, if I put a load here, for example, in the center, we put any load there because they were this smooth, they will not bind on, they will slip relative to each other on the surface. So of course you can see by yourself. You can see use two smooth ones put together, put every load, they will slip over to each other. But if we bound together, if one is three boards again. But this time we use some way, use glue or use nails or use anything put together. So let's say it's a bonded together. Then we put any loads here. You will see they have no relative movement. They just act as one entity, just as one board. So this is typical for many locations, these things. So it's why for here, they bound together, but they were put together. But why we should bond together? If this one is no anything there between each other, so then of course they will not move. But actually, because there's some loading between each other, so that's why they will move. That's the one effect because of the associate longitudinal shear stress. Because of the transverse, and then where longitudinal also have load. That's why here between each board there's shear stress between each other, but in a longitudinal direction. So that's why even there's no bond together, they will slip over each other. But when bound together, of course, let's resist the shear stress. So that's why they will bound together and act as one entity. Okay, so that's because of the thing. So entity, that's what we also can say is a single unit. So this is very common. If you go to any location, you will see some kind of case. Okay, even for this, look, everyone look here. Look for this side. All this one is glued together. Okay, this guy after class you can see this all these things. The board just is glued together. Okay, so it's why this is what I mentioned because of the presence of this shear stress, the single solid beam is much stiffer and stronger than to separate beams. So that's why for most engineering projects, we use different beams bound together. They can use different things, use rivets, use nails, use screws, use glues, use welding. There's so many different types of things. That's why we later on we understand these things. Okay, so how we can understand this thing? So, as I said, we can assume these things on the structures. There's one thing on the ground for the transverse, but also the longitudinal direction have a same magnitude we know before. Okay? So from this way, we can understand, we will assume that structure will be on the same width, will keep the same, but actually only change on the locations, on the position, relative to the neutral axis. So for a small element, we can assume that the shear stress tau is uniformly distributed across the width of the beam, although the may vary over the height. So there will change on the height relative to the neutral axis. So we know before for the fracture formula. Okay, so that's why from here we can get this idea. We can get all the things. The transverse is complete with the longitudinal shear stress and the same magnitude due to the equilibrium with the transverse. Of course, I just let you know where it come from. I will not ask you to deduce these equations. Okay, just you know where it's come from. You can get an idea. So then also, of course, based on this one, they will come together. Or as I mentioned, on the top, on the bottom, there's no shear stress. That means for all the things we go up or down, there's also relative location on the transverse will also zero. Okay, get the idea? Because on the top, on the bottom, there's no shear stress because of free surface. So that's why for the same way as this. So all was this, as we learned before. So that's why they are perpendicular to each other, but they have the same value in magnitude. Okay, so we learned before. That's why you didn't know. You just summation fx equal to 0, summation fy equal to 0, summation m about 1 point is 0. Okay, because they should be in equilibrium. So that's why it's very easy for you if you understand these things. So now, of course, these things we can get an idea. This one we can get any location it will change. We can get a transverse. So that's why for here we should use the shear formula for these things. So they have the same magnitude in their vertical and also horizontal shear stress. So that's what I mentioned before. They should work to each other. So for supplementary. So of course, based on these things, then we can get any location. So for example, of any point along the beams. Okay. So now of course we just find 2 points. One with the location about the x, and then have a little small derivation of a dx. That's what we can see from 2 parallel cross section. So one is a v up, is a v down, and a cross section. This is what we see from lecture 2. So definitely this is a positive value. Okay, so that's what from here, so we can get this as a positive value. So it means a v and a v plus delta v just small and even change, and also m and also m plus dm. Just so you can see the value change of these things. Of course, based on this one, we know from the fracture formula. So this one will be resolved for normal stress because of a bending. Clear? So that's why from here we can get an idea because of a bend or from the moment. So there's a fracture, okay, equation. So that's why from here all summation of fx will be 0. Okay. So that's why from here we take any of this. So we see we take any location from the say position y1 relative to the neutral axis, the x. So that's why from here we can get this y1 location to the outer surface. We can get any of this. So then we can get anything the sigma 1, sigma 2. We can get it sigma 1, sigma 2 because of the moment. You still can remember we have a fracture equation. Okay, that's why from here, this one, sigma 1 is a negative m y1 over r. Sigma m2 is m plus dm y1 over r. So of course, this one y is the distance from the neutral axis. That's what we from the fracture equation. Okay, and r is the moment of the inertia. Put the text here, entire cross section. So this means here the whole cross section. Clear? So this, you must know this thing. That's why I will not ask you to deduce this equation, but you should know where it's come from, because it's from the fracture equation. So that's why from here we can get this in sigma 1, sigma 2. So of course, based on this one, we can see here, because this should be equilibrium. So that's why there must be one shear force exist here. Everyone clear? So because here I get more, here I get less, the dm. So from the value is a positive value, okay? So that's why there's one tau for shear force. So that's why we can see from different view. That's why from here you can see there's a y1 and a location of this. So then later on we can get any small locations. Then we see the width is a b, and also we can see sigma 1, sigma 2 from other slides. And then we can see sigma times A will be the force. Remember, we say we must work on summation F will be equal to 0. Not summation sigma will be 0. Clear? Because it's sigma, that's what we should convert in F. F is sigma times A. So that's why we can get anything here. F1, F2, and F3 for the shear force. And they see from next is Y1, this is the half H for this one, if this one symmetry. So from here, we can work out for the integration of the values. So F1, F2, we can get a thing. You see, integral Y1B to the half HB. That's an area, that's the height, area. Okay, so sigma 1 dA. And sigma F2, we can do the same way. Okay, so what we can get F1, F2. Same way for this one, because summation all the Fx will be 0. So that's why F3 should be equal to F2 minus F1. So this is basic thing from math. So then from here, we can work on F3 is a dm over r and times integral y1b to up to half hb for the yda. So then we can work on this thing. Remember, F3 is tau A. Tau A is a tau B dx from here. You can get it from that. It's B and dx. That's why from here we can get this value. So from here we can rearrange these two equations. So that means we can get a tau is a dm over dx. So that's a derivative m with respect to x. Okay. Now 1 over rb times y1b half hb and yda. So integral. This equation don't worry too much, but should the meaning, that's the most important. That's why highlight in yellow here. So this one is basically where it come from. Then you get the idea. When you do calculations, you should know where it come from. Okay. The y is the measure from the neutral axis because the equation is reduced from the fractal equation. So that's why y1 always from the neutral axis. That's from previous one, same, okay? And of course, this should overall over the cross-section area. So work on the P1, M1, M. So that means from Y1 to the half edge. So that means from the location to the outmost. Clear? So from Y1 to the outmost. So for example, from here, you should get the idea. And the Y1 is the distance of the interested. So which point we are be interested in. Okay, located at the from the neutral axis of the whole cross section. So of course, I we should know is from the whole notion of the whole section. So of course, we can do further simple work. If we can remember, shear stress is equal to moment over arm. So that's why V is a dm over dx. So that arm, we can further put this thing in. Here, dm over dx become V. So the one here will be V over RB and put this thing together. But remember, here is also a similar way as we mentioned from the lecture 2. Okay, also for engineering mechanics. This is a Q, Qx. Qx is equal to YdA. If you can remember, you can go to the lecture slide. But let's just review. This is for engineering mechanics and also fix. If you learn physics from school level, you should also know this thing, okay? But that's for engineering mechanics. So Qx is YdA integration. So from here, you can get a similar word. So the Q from Y1b half b HB YA, this will be Q. So the Q is the first moment of a rectangular area of the width B and the height of the MB or M1P1 from here. That means from here will be from location or the whole things. So tau is being derived from the neutral axis and it's not relative to the whole cross section. That's should know where it come from. Okay. Remember, I will also reduce, but you should know the meaning. So when you do the question, you should know where it come from. So then you can work very properly. Okay. So of course, when we get anything here, then we get a simple work. Tau will be equal to VQ over RB or RT. Some of the thickness could be width or thickness will say this is T or B. Okay, that's because of the location. So from here, yeah, that's the equation, much simple to work out. So that means tau is equal to VQ over RB. Okay, but the main thing is the meaning of the symbols. So that's the most important. Okay, don't think I put the equation. No, you must know the meaning of this. So tau is a shear stress in the member at the interest. That point located from the distance to the neutral axis, but from distance y. Okay, so that's why for this one, V is a shear force. So this one definitely will work out from the method of section. So that's why we should link all the things come together. Okay, so while here we can work use the method of section, you will get a V, and the I is a moment of inertia of the entire for the whole cross section, okay? Of the whole cross section area get about the neutral axis. And the BOT, because different book, some use a book, use B, some use your T, okay? That's what you know. The width of the members cross section. So, of course, measured at the interest point where B or T is to be determined. So this one is very important for you, okay? Some key point I must highlight to you. So, one is a B or T. You should know where's that one. This one from the location you are interested. So we will use an example to show you, okay? So that's why this one you must know where's come from. That's very, very important for you. And the V, this one must from the method of section. If it didn't give to you. From the real project, you must use method of section to work out. That's why I mean a lot of times method of section that will show the immediate enzyme and the final enzyme because it's so important and the basic thing for you. Okay? Then I, number 3, I is for the movement of the inertia of the whole cross section. Doesn't matter where you are interested in, but for the whole cross section. Okay? That's why for these things, it's key thing for you to know the meanings. So that's why I highlight anything in yellow. You should know that's very important for you to understand. I put many text here. I want you to know the meaning, how you can work out. Okay. Even we know these things, we use the way where it come from. So that's why we should know this is the way we can work out for the normal stress from the horizontal. But actually, because they are supplementary to each other or complementary to each other, so longitudinal direction, transverse direction should be equal in magnitude. That's why for these things, we can work out the whole section of the cross section of this structure. So that is here applicable for finding the shear stress acting on the beam's longitudinal plane and the transverse shear stress on the beam's cross section. So that's why we work on any longitudinal direction or work on the transverse direction, we can use this equation. So that's why I ask you should know where it's come from. I will not ask you to deduce, but should know where it's come from. That's it. So then we should know the meanings because from the way we work out. Okay, so that's a way for you to know these things. So that's why we should have an idea. This is the way for us to use. So that's before we use, we must know some very important difference. So of course, important points to use these equations. The tau is VQ over IB over IT. I highlight BOT because these two are so important. So the location. Clear? So the width of the location. So that's why when to real project, you will say, hey, this thing seems the same, but actually the values will be different. Okay, because the location width will be different. Okay? Of course, shear force in the beam cause non-linearly shear strain distribution. So, of course, causing it to wrap depends on how much difference of these things. Second one, to the complementary property of shear, the shear stress developed in the beam acts over the cross section of the beam and along its longitudinal planes. So that's why we should know this one from the whole plane. Okay, so of course the plane could change the cross section during the application. So but we should know this can be applied for all the things. So of course the shear formula was derived by consider horizontal force, equilibrium of the portion of our different segment of the beam. So that's why we should know where it's come from. Then for this thing, we should do the solve problem. We can work for the real problem so you can get the idea. And then the shear formula is to be used on a straight prismatic members made of homogeneous material that has a linear elastic behavior. That's for most engineering problem will be homogeneous material. Okay. Also, the internal result shear stress must be directly along an axis of the symmetry for the cross section. So this is typical for engineering project. So the most symmetry. That's why it's very useful calculation. Because we mention these things, look carefully. For symmetry parts, this one is half, also bottom half. So that's why for symmetry, for the project, we can work out. And of course, there's some condition to use. The shear formula should not be used to determine the shear stress on cross-section that are short or flat. If this is too short, the value could be a lot different. Okay, that's why we should be careful of this thing. At the point of a sudden cross-section change, we cannot use this thing because the structure, as I mentioned before, the shear force, the value will be totally different. So you can remember, we always use some stress concentration factor, if you can remember. Okay, that's why for this thing, you must go anything. So anything, so we should think about. Of course, we can apply this equation for composite beam. This is typical, very, very powerful, okay? So, but remember, composite beams will be from different 2 materials or 3 materials or some other thing, but at least 2 different materials. But from here, we say that's must from homogeneous as a linear elastic behavior, a single material. So that means we should know how we can transform composite beam to a single material beam. So that's why we should have the idea. So that's why the question will combine to each other. Okay? So composite beam, combined this kind of thing together to work out. So that's the basic thing for you to understand. Okay, we can use one example and 2 examples. We can see what happened over here. For example 1, so determine the distribution of the shear stress over the cross-section of the beam shown here. So of course, this question asks you to work on the distribution. So that means on the cross-section, we can use the equation to work out the whole things. But remember from here, the cross-section of these things, we can get an idea where it's come from and where's the neutral axis. Because from the equation, we must get the idea the neutral axis, then where's the location of this. So that's why from here, we can get this idea, we can work out these things. So we can work out the thing to work out. So of course, we can get these things done from different location. So we know the width is B, height is H. This is rectangular. Of course, the symmetry. So that's why we can get this thing to find the neutral axis, and we'll work on the whole, the I for moment of inertia of the whole entire cross section. So then we can work on the Q, and the V will tell you. So that's why from V will tell you V. So that's why we should get the idea for the Q. Q, you will get any location. For example, if it's a Y, so then we can see where's how much of the Q. Everyone should know this thing. The Q, we have the idea is Y bar times A, summation of all the things. Y is the centroid of the components. For example, we know that any location of the Y, then we see from the Y to the outermost. So that's we from these shaded parts. Any question here? So remember, all the things will start from here. For any location, location Y1 to the outermost. Clear? To the far to neutral axis. So from here, if we can find any location, so now of course we can Y to the outermost. So that's why it's a shaded part of these things from here area. So of course this is also rectangular one. So the Y bar A is Y plus half of the half H minus Y. So that's why this is the centroid of the rectangular. But plus Y, that's the relative to the neutral axis. Because neutral axis is a half of this thing for this rectangular. So then the area, of course, this one is a half H minus Y is a height. The width is a B. So we can rearrange. You can work on like this way. So the same way, okay? So then later on, we can apply the whole thing. The tau is equal to VQ over RT. So the V give to you, Q, we just work out. I is the whole thing. You should know it's a rectangular one, is a 1 over 12 BH cubic. then times this one is any location with the same width. So that's why here is a B. So that means we can arrange and we can what thing. This one actually we can find distribution is parabolic like this way. So we can use the function to work out. So from here we can get the wax maxima, wax minima. You can see if y is equal to half h, this one will be 0. That means half h is on the top surface or the bottom surface. If this y is 0, that means in the neutral axis, this one will be maximum. So that's why we can get this value to work out. So the tau max will be equal to this value we put together as 1.5 v over h a. So that's why from here you can see the tau max is equal to 1.5 of the average shear stress. Clear? So now, of course, we can get this value, see, like this way to work out. It's 0, 0, maximum. So we can get these things. So that's why the change from different, there were a lot of homogeneous along the height. Okay? So, of course, based on this one, we still should know there's still some limitation of this. So the shear stress formula was derived using the fractional formula, as we mentioned before. So that's why the material has to be linear and the same modulus of elasticity, intention, or compression. So for constant beam, of course, we should transform this kind of structure constant beam into a single material beam, okay, before applying the shear stress formula. So actually, for many applications, we should do the same way. Transform the constant beam into single material beam. Okay? So for these things, we should know that shear stress is a uniform over the width. Okay? With a B of these things. So that's why we can compute all these things. But remember, this is also an average value. So tau equal to VQ over RB, and one height along the width actually also average value. Okay? So for example, if anything here you can change. If this one is the HB of this thing is a H much higher than B. This value you can see there's roughly change. But when it's white, so that means the B is much higher than H. So then this value will change a lot of these things. So actually the maximum always happen on the edge or sides of the beam. So actually, so that means the shear stress is not uniform over the width. So there's a maximum value and a minimum value. So the maximum value always occurs along the sides of the cross section. And of course, the maximum will be depends on these things. The B over H. If the B over H is about 0.5, that is only 3% difference. But actually, if the B over H is 2, it's about 40% greater and much more different. So that means if this one is shallow, okay, so that means from the B to H, so width over height is small. This value is accurate. But the B to H is larger. This value is not active. Okay, so that's why from here, we must get this idea. This one we cannot use for the white plate. But actually in industry, we can use a lot of it because, for example, if it's a white fringe, but because in the center one, it's very small in the width. So that's why from B to H, this one is still very big. So that's why from here, we can get this idea. So that's why from B to H, this one will still can be used for calculation. Clear? Because this one, B over H, this one, B over H is also very small. So that's why for here, still, we can use this thing to work out. Okay, that's why for here, we still can use this kind of equation to work out the I-beams structure. So, of course, how can we work these things? First thing, we should use the method of section, okay, to do the work, to find where's the internal stress. Then later on, we can find the property, section property of the R, so moment of inertia for the whole structure. Then we can imagine the horizontal through the point where the shear stress to be determined and measure the width of the cross section at the point or inches the point. Then later on, we determine the first moment area. Q is the Y bar times A area. So because this one will be from the location to the utmost. Okay, so from here we can work out. So later on, we can use the equation tau is equal to VQ over RT to work out the tau. So remember, that's the way we combine so many things together. That's why you feel harder and harder. Okay, we combine many things together. So lecture 11, most difficult. That's for industry project. That's why for final exam, I will not ask you to test lecture 11. Okay, that's so hard. Okay, but remember, so real project will combine all the things together. But for exam, we'll just divide something for simple topic for you. So that's what you see. If you don't understand from beginning, the whole unit you cannot understand. Okay, so we now use that one example to show you how it can work out. A steel what French beam has the dimensions shown in the figure here. If this is subject to a shear force V, will give to you equal to 80 kilonewtons, plot the shear stress distribution acting over the beam's cross-section area of this. Will give you all the dimensions of this I beam. So for I beam, we'll plot so many of this, so you should know how you can work out the moment of inertia. Clear? This is what you must know. This basic skill. And where's the neutral axis? So of course, based on these things, because this structure will be here, we can see this I beam here and here and here. So that means we can see the structures will be different. Okay, so that's why we can work on the web, we can work on the fringe of this. But because this is something different, so we see the one point it's a fringe, and in the next thing at the web. So that's why we can get only things the center and the edge, but belong to the web, and also edge belong to the fringe. So that's why we can see such kind of thing. So of course, we should first work on the whole moment of inertia. So this R is equal to half 1 over 12 BH cubic. But we should work this in. I will not work this again because we had so many such kind of practice. Okay, so that means we can work on the I for the I beam. Later on, we should find the different location for interest. For example, for the B prime is in the fringe. Yeah, remember on this side. So there, of course, how much will be there? So remember, we will use the equation tau VQ over RT. So V give to you, I will just work out T, the thickness, 8, the interest point, okay? The Q is from the work on the Q from the point to the utmost. That's why from here, we can work on the B prime is on the fringe. So that's why T B prime will be how much? 300 millimeter. Clear? So because B prime will be in the fringe. So as we here is a 0.3 meter. The area, that's easy. This area just above. So that means here we can work out. You see, is a 0.3 times 0.02. So, but how much of the centroid? Centroid is in the center of the rectangular. So that means here, so from neutral axis, 0.1 plus half of the 0.002. So that means 0.11 millimeter times the area 0.3 times 0.02 meters. Here's wrong. Here's 0.02. I put the wrong way here. Okay, so that's a mistake here. So that's why you can work on these things. So that's why for the area of these things. Yes, it's 20 millimeter. So that's why here I put a little bit wrong here. So that's why from here you can get this number. So this one from lecture 2. Clear? So that's why we also from engineering mechanics. That's why we should know these things. So that's why from here we can work out the tau B prime. Everyone look carefully. Look on the screen carefully. Okay. V QB prime over RTB prime. Yeah. So VQ over RT. So that's why I put the values here. V gives you as 80 kilonewton. QB prime we just work out. R for the whole thing here. T prime as I mentioned because in the fringe. So that's a 0.3 meters here. Look at the number. This is very important for you. Okay. Everyone look on the screen. This is so important for you. This is 0.3. So use calculator, you can work out. Later on, for B, look for the B. B is in the web. Okay? So everything here, VQB over RT. So because this was just in the same location, but one's French, one's web, so that means the QB will be same as the QB prime. Clear? Everyone clear? Okay, but the main thing is TB. TB because in the web, how much will be here? The web here, 15 millimeter. Clear? So the one here is a 0.015 meter. Same location, but one belongs to web, one belongs to fringe. So of course this value will be different. Of course this value will be different. So the web here has more shear stress. Everyone clear? So of course we can do the same way at the C point in the center. So centroid. So of course for the centroid, which is the QC, there's a 1 for rectangular, 1 small rectangular, another one can Q. We work so many of this, you can work out. Okay? So 1 bar times A. So for the top, same. Bottom one, you see half of this value. So that's why I can see half of the 0.1, so 0.05 times 0.015 times 0.1 is the area. So that we can work out. Same way, we can work tau C is equal to tau max is a VQC over RTC. So V give to you Q, which is work out. I is a whole thing. TC is in the web, is a 0.015. So the Y is a 25.2 megapascal. So the Y from here, we can work all of this. It's a parabolic, but you see the change from the web and the fringe. The value for the point will be different. Okay? So the Y from here, we can work out. But you can see the average value. The average value will be 26.7. You can see the area of this value. So you see the average value is the average value. Clear? So from here, we must work on the question for the Q, for the I, for the T. This everywhere should be pay special attention. Okay? Okay, we just have a 10-minute break, then we'll come back for the next parts. Okay, we'll continue. So actually, we have this idea where it's come from for these things, for this equation, okay, for the shear, for the transverse shear stress. Of course, we mentioned could be used for the horizontal and also the cross section. So actually, in engineering practice, so a lot of members are built up, okay. So that's what we call this one built up beams from the composite parts in order to achieve a great resistance to loads. Actually, built up are fabricated from 2 or more pieces of material joined together to form a single beam in order to achieve a greater resistance to loads. So that's for resistance of the loads. So that means we should put many together. That's why for many boards were bound together. So I said either by glue, by nails, by screw, by rivets, so many other things. So actually for these things, we saw a lot of different things from the structure. So here are some examples to show you. 3 examples. This one is a box beam, and one is a glue lamp beam, and also plate girder. So you can see from here the box beams of these things. You can see a lot of here. For this one, these structures. So you can see from here. This one from wood box beams controlled from 2. You see from here, there are 2 planks, which serves as a flange, and also 2 plywood. Okay, there's a plywood. That means you can put it as a web over here. So there are 2 solid and 2 plywood for these things. So actually for these things, so these are joined together. So could it be, I said, could it be joined by nails? Could it be joined by glue? Could it be also screws? And also for many of these. So actually for this one, just next a box as a whole structure, just as a box. So that's for these things we can put it in, has a lot of things for here as a beam, put a nails, put screw. If you go to for example, for some furniture shops, so actually many furniture shops. So for example, IKEA or anything, you buy the your bed, buy furniture. So depend on the cost. So you will see a lot of pin together, something like a wood put together. Just use wood pins inside. Okay, that's all for this. Very common for all of these things. So it's better for the industry. But our second example is the glue lamp beam. The glue lamp beam, that means there's a one word for glued laminated beam. So that's why I say glued laminate beam. Okay, typical this structure for the bench. You will see from here is a glue lamp beam for these things. Okay, because it's a glue to put together. Okay, the third type one is plate girder. Plate girder, so it's very common in the industry. So of course this one, so it's better for the bridge and also large buildings where you use this kind of structure. Okay, so for these girders consist of 3 steel plates, 1, 2, 3. So use this thing. But actually this one will use the joint by welding. Here is welding for these things. So of course this can be produced for large part. For example, it's a lot of large part, but it can use plate with together become large part. That's much easier for the construction. So of course they were finally where doesn't matter how many you put together, but they were finally they become one unit. Could be user structures. But they will say, oh, that's the easier way to do it. No. So I say depend on your cost. For example, your furniture, the cost less, I will tell you that's life will be very short. Because this kind of way put together, the design is not well. Okay, because not strong enough to sustain. That's why later on we can show you how this thing will be happen. Okay. So of course, design such kind of calculations. So result revolves in 2 phases. First one, the beam is designed as a though it is made of one piece, take into both bending and shear stresses. So the connection between the parts, as I said, lots of layers, bolts, wires, and glues, and so on, are designed to ensure that the beam does indeed behavior as a single entity. So that means if it's not strong enough, it's very typically for those cheap furniture. Okay, otherwise your chairs, your computer desk, if it's cheap, you will find some use it was shaking. Okay, because this one is not designed very well to ensure the beam does indeed behavior as a one entity. It's not strong enough. So that's why for cheap furniture, the life will be very short. Okay, that's because of the design inside. But how can we work this thing? So that's before we do, we should know in particular, their connection must be strong enough to transmit the horizontal shear force acting between the parts of the beam. So to obtain this force, we make use of the concept of shear flow. So that's what we use for the design. So we find how many pins will be inside, how strong will the pin will be there. That's for the design. So then what is the shear stress? Shear flow. So shear flow is reference as the horizontal shear force per unit length. Okay? Along the longitudinal axis of the beam. Please check the highlighted words. Okay? So shear flow is horizontal shear force per unit length. So along the longitudinal axis of the beam. So please note that this is very important for the highlighted words because otherwise when do calculation you'll find different. For example, here's per unit length. That means this one should divide by the length. Okay? So that's the value over here. So of course, this thing that we can see can use for to determine the shear force in fastener glue which holds various pieces of the built up beam. For example, here's a furniture. Here furniture how many? It's 1, 2, 3, 4, 4 boards. But all 4 boards will be glued, okay, or by pins. So the one from here is typical for here. So of course, using this thing, using a similar procedure as we share in the last part, beam, we consider anything of the shear flow between of any location. For example, any locations of the location. So x or dx, okay? So that's why I can get anything here. Consider finding the shear flow along the juncture where the segment is connected to the flange of the beam. Then later on, we can get the word horizontal stress. So F dF, okay? So of course, here we can see the normal of here. So now, of course, the third one should act as the juncture because of the difference of the loads. So this is the same as in the last part, okay? So of course, definitely we can get this equation. dF is dmr, so A for the whole area, so YdA. So that's why we can get these things. So this same thing as the last part for shear stress. So that's why from here, after we know these things, then we can find the shear strain. It's better for the rectangular one. So these things, that means for the shear flow formula, we can get anything here. So that means horizontal shear force per unit length along the longitudinal axis to the beam. So that means from the definition of the shear flow. So now from here, of course, we can work out how much we can work out. So of course, the equation we mentioned to you use a shear flow. How we can work out? You will see everything calculation was from previous one, but this was just per length. Okay, so from here, we can still use this way to work out. So for these things, that's from last parts. So now we can see the parts we can work out based on F1, F2, F3. We can work on these things. Summation of all Fx0. So now, of course, we can work on this part. But remember, as you said, the definition of the flow is per unit length. So that's why we should divide by. When we stop here, we can work out it's from last part. But because we should by unit length, because unit length is x, that is here f is equal to uppercase F over x. So that means from here, the F here is F3 divided by dx. Here the length, yeah? So that's why we can get it here, get this value. Same way, this one is Qx, as we know before. This one is a V. So that's why from here, the Q is equal to V Q over R. Look carefully here. So the Q is a shear flow. So that's why from here, we can get this idea. So this is different from the previous shear stress. Clear? So that's why from here, every definition will be same as the last parts because use all the way to work out. But just because there's an X position, we should change for the dx of this. Okay, and so from here, we should need an idea. Everything will be same as the last part. The way we work out will be same. Everyone clear? That's why here I didn't give you more details. This is from the last part. So of course, I will not ask you to derive all the things. Just let you know where it's come from. Then you get an idea. Hey, this one should do something. This should do something. Okay, that's what you understand. Not just say, hey, why you didn't put your questions in front of tutorial questions? So we're not ask such kind of interesting question. Okay, so from here we can see the shear flow Q is equal to VQ over R of these things. So we'll come to these things, but you must remember for this thing, as I was saying, where's the A is so important. Where's the location interest? Not like from previous one, we show, hey, this one for anyone we can do. But for the built-up beam, we should know where that location should be. Because that for pin, for rivets, for boards, for screw, for weights, there's many locations. So that's why for this thing, the areas used for calculating the first moment is very, very important. We should find out where we should find the interesting location. For example, for this one is a steel girder here. So of course, it's weight. Of course, this one definitely will be passed through the location. This one definitely pass the location. If you put here, sorry, this is the wrong location because we should put the weights there. So that's means two weights from here. This up flange, this one horizontal one should pass through this location AA and also this thing. That's why this location is the interesting location. Clear? So that's why from here, I put a comment here. This one at the up flange, the horizontal shear force per unit distance along the axis of the beam is the shear flow along the contact area. So that's why as a shaded the parts we use for A. This is the A for the shaded location over here. Okay, that's why I say the shaded segment in each figure is used for the calculated Q for this. Okay, second one for this structure, the wide flange beam. This one because they will put here rivets or screw. You can see here. This will pass through this thing will be used to resist the shear flow. So that's why for this location will be interest. Clear? So that's why for this and this. That's why here is change the parts will be used for the BB. Same way, for example, for the box. For the box here, you can see this one uses screws. Of course, this one pass through. So that's why for this location we used for the area for calculations. So that's why CC or DD were used. So that's why for here, we should know which area we used. That's very, very important for this specific thing. Not as a last part. Last part we can find any for distribution, but for the built-up beams, we should know where's each part. That's mostly used for calculations. So that's why don't confuse this part and the previous parts because they have a more specific area. Everyone clear? Okay. So when do anything here, of course, we know we should use a pin or screw or something. But how many we should put? Not only one. Okay, maybe two, maybe three, maybe four, maybe other things. So we should find here, we will choose, hey, have a good future. We'll put many distance, same distance of these things. That's why we should say fastener spacing. Okay, fastener spacing is the spacing S along the beam when beam segments are connected by fasteners. For example, by nails, by bolts, by any other things. Okay, so for example, here. This one for the bolts, okay, or nails, depends on the structure. Here's nails, okay. If build nails here is put one nail here, of course they just block the shift. But maybe here you say how many? 1, 2, 3, 4. There's so many other things. They will put so many together. Okay, that's why from here we should find the location of a distance. Okay, that's why from here we should find out each of them and how many will be used to fixed. That's or called resist the shear flow. So the one for nails are used to hold the top board of the bottom, so that no slipping occurs during bending. So that's a fully second case where force is equal to QS. Look carefully here. F is a force. Q is a shear flow. Shear flow, that means the force per unit length. Times S, this distance. That's why here, same, force on both hands of the equation. Okay? So F is in newtons, maximum shear force before it fails. Q is a Newton per meter shear flow between the bend and the boards. S, the fastest spacing. That's why from here, we can get these things. But remember the one thing, there's put many together. There's many type of the boards could be. So of course, for you guys can see, if you go to building one, a lot of Gerard beams, yeah? You can see building one. Between is a lot of screws. That's why you can see, you can check how they put an equal distance for each of them. Okay? So you guys can go building one. That's easy for you to see these things. So now from here, they put anything here, how much will be this? For example, we'll work these things. For example, this structure, we can put these things. Hey, this one is on the top. So this one I have a 2. Let's have a 3. So now how can we work these things? So as well from here, this one, this could be 2, could be 3 of this. So let's put text here. This is very, very important for you to know, okay? So the shear flow here must be found at the thick black line, okay? And it's determined by using a value of Q calculated from A and Y indicated in each figure here, the distance. A single fastener supports the calculated value of Q. So that means only for a single fastener we use a Q. But with 2 to support, for example, this is a 2. Then of course this will divide into the Q will divide by 2. So that's why here there's a half Q for each. If a 3, that's a 1/3 of Q will so send for each of them. Okay, that's why we should get this idea to work out. So we can use the example to show you. Okay, so this is typical industry applications. Here, I'll put it one slowly, okay, because it's very important for you and also very important for exams. Okay, that's why I've give you more details, how you can get it, these things. Okay, of course, I still highlight in yellow on the top to let you know. But remember, the question will be like this, okay? But knowledge will be same, method the same, just you should understand the structure. So don't complain, why don't you use the tutorial lecture question? Definitely not, okay? So this one is nails have a shear stress of 900 newtons are used in a beam that can be constructed either as a case 1. Case 1 is 3 boards, yeah? Or as a case 2. Case 2, 4 small boards and 1 big board. But they were fixed by different way. Okay? So if the nails are spaced at 250 millimeter. So for example here, 1, 2, 3. This means they're spaced for this one, same gap. Okay? Determine the largest shear that can be supported in each case so that the fasteners will not fail. So that means this one, the sustained, the shear force should be equal to each other. Okay? But because from different design, the stress sustained by the nail will be different. So we'll see which one. So of course, sustained higher or lower. So of course, in the higher, that means they have more opportunity to broken. If it's sustained less, that means if the room is large, it's more safe. Okay? So that's why we can check this situation. Of course, you can see the dimension only give to you. So let's same way. Okay, even at two same over here. That's why we definitely will know we should work on the R. Clear? Q shear flow is equal to V times Q over R. So that means we must work on the R. R is for the entire cross section. Everyone clear? So this one you must know this thing. So then that means for the two design, we must put the R. The dimension same. So that means the R will be same. Clear? So the R will become the same for the R being. Doesn't matter how to put it, the R will be same for these things. So let's see here, you see here, the things 10, this one, how much? 80 and 10. That's the total is 100. This same thing is 100. Clear? This is 25. This is also 25. So that's why same R being, but doesn't regardless how they design the structure, but the R will be same for the shapes. So that's why for this one, we should work on a moment of inertia of the structure. So this one is IP will be, you should work it very easily, okay? So I will not repeat this again. So hopefully you can get these things, okay? So if so far still not work, don't know how to work on moment of inertia, sorry, I'm 100% sure you will fail the unit. Because you can say every question you should do these things, okay? So after we know these things, so then we should find here for the case 1, case 2. You will see how the difference will be. So for the design of the case 1, these are 3 boards. One is on top, one is on bottom, one is for the web. Okay, but use pins to put together. So for this design, a single row of the nail holds the top or hold the bottom of these things. So that's why for this one, we should on the Q. Q, of course, will be on this location for this thing. So the mention here, you see, that's the location for the pin or nail end over here. So that's why from here, we can get anything here. That's where we work on this structure, on the pin. Okay, for the pin. So that's why it's Y bar A. Okay, that's for here. So that's why from here we can work out. It's 0.045 times 0.055 times 0.1 thickness of this. You see from here, because this R beam, that means in the neutral, it's in the center. So that's why from here, the center one, so of course here, 80 divided by 2 is 40. That's why 0.040 plus half of this 10. So that's a 0.045. Okay, the area, you should know how to work out this area. So there's no doubt, it's quite easy to work out. Okay, so that's why from here, we can work out the Q for this structure. So later on, so we can see this lowercase q, that is the shear flow, is equal to VQ over R. So of course, we can get it from here. The Q, the maximum will be 900 Newton divided by the distance, 0.25, equal to VQ over R. Q will just work out, I will work out. This is the V. That means this one can sustain shear flow of 439 Newtons. Clear? Same way for case 2. Case 2 is much more complicated because the beam is only big beam, but it's 4 small plate. So what is a pin here, pin here, pin here, pin here, pin here, pin here. That's a pin. So what from here, we can get these things will be the shear flow will be on this location. Clear? So what from here, this one will be different. Everyone look on the screen. This is very typical for you to know. You see the Y bar will be same because it's always in the center way. So it's halfway to this halfway. So that means 0.45. There's no doubt, yeah? But look at A. A because for this small part. So that's why here, how much over here? This one is a 10 millimeter thick, but long is a 0.025. That's why here is a 0.025 times 0.01 of this. It's the area. But look for here is a 0.075 times 0.01. That's different of this area. So this one only for this. This is one for the whole plane. So that's why from here, the Q is different. Then later on, we can still work on here. So locus Q is a VQ over R. So 900 divided by 0.25. We can work on the shear flow, how much will it be. But remember the Q here is a V is a 0.32 kilonewton. Because this one has low shear stress. This one have a large shear stress. So of course, you see the case one is was fastener away, which about 3 times lower than the case. Okay, because this one can sustain less of this. This one can sustain half of this. So this one will be more. This one, because you can see this kind of should have more of these things to sustain. So that's why for many boards, if it's heavy, so we should know how much will be due. Because this one, for each of these, they can sustain. If say they have a 900 Newton of this, they can sustain higher. So that means they can maximum sustain these things. So they can maximum sustain this one. This one is not good design. This one is better for these things. So for the design of this one. But this depends on the structure itself, okay? But for other things, for bending, for other things will be different. Not only for this kind of case, for these things. Okay. This is just for one thing of this thing, so that you know the structures itself. So that's why for industry, they will not put these things design. This design will use a lot of more other things to put the designs. Okay, we do anything here, so actually we can see other things could be. So basically, we do anything here for design, for all the things, we'll continue put all the things for the structures. But how we understand the shear flow distribution through the whole members or cross-section area? Because it's the width is for the width with the most structured beams. So we show the beams with very thin walls. So that means the wall thing is small compared to the height and the width of this kind of structure. So before we determine the shear flow distribution, we will first show how to establish the direction of these structures. For example, this kind of structure. This one structure is very common for I-beam for these things. Okay, so that's why from here you can put a lot of things here. Can put the structures for this. See, from each other, they can have different flows of these things. So that's why we should draw free body diagram. Then we can work all these things for the complementary, for transverse, components Q. So then we can get all the results over here. So although it is also, so for example, for the V and then VdV, so for the structures of here. For example, for this one is a V plus dV, so that's a force. Even though so, they were something for calculations. But of course, we can put the force itself, the F and VF plus DF of this thing for the cross section. But how can we change to each other? So that's why from here, they must work on the cross section area from the complementary for the vertical and also horizontal for these things. So of course, based on these things, we can work out a little bit for the shear flow from different locations. Okay, so of course you can see put here the effect of a vertical shear flow component for these things will ignore. Okay, because the flange is thin and the top of the bottom surface of the flange of free of this thing will be free. So of course that's the only shear flow component that actually parallelly to the sides of the flange will be considered for this situation. So then of course we can see how this thing will be happen. For example, for this one for the beams here, this one for example is a shear beam. Then we can see from different location, we can see on the flange. We can see different location, we see away from the central. So that's X. From the X here, of course, we can get the thing, the stress, we can get work on here. It's a Y bar and also area we can work out. The Y bar is a half D. This one, the area is half B minus X times thickness. So that's why we can get a Q with VQ over R. So we can get this number. So from this number, of course, X is equal to half B, that means 0. So half B, that means the H. So it will be 0. You put it in the center, of course, is X 0. So this will be maximum value. So that's why from this value, we can work out this number. So that's why from here, we can get it. So same way, of course, we can do the bottom one. So this is 0, 0, and a large. So from here, we know from previous one, this is a web. Web is a parabolic. On the neutral axis, there will be largest value. So that's why from here, they will flow this way, go down, then go to this way, become the 0. So that's why from here, we can work out by the whole force Q dx of this direction. We can see that the Vt dB square over 16R of this value of these things. So of course, if by area, you can see this value same. You see, if by area or by integration, the value will be same because this is a rectangular. That's quite easy for calculation. But doesn't matter how we go. You can see this one will be from this way, go, and then we will go down and go up. And flow like this way. Same, we can go for the web. We can see only from any location. So we can see from location Y. We can also for the Q, the two parts, one on top, one is the middle of this. So the two parts, one part, another part of this. So we can work out. So that's why for here I will not go detail. So everything will be same as before. So now of the Q is VQ over R. So V give to you the Q, of course, we give to put all the things together. So the T take out. So that's why we can see that's this number. Same way we can see if Y is equal to 0, we will go to maximum. If we go to half D, that means we will go to 0. So that's why I can see from half D will be 0. Go to neutral axis will be go to maximum. So that's why from here we can get this value as this. So you can see it's a chromatic. So parabolic for many of these things. We can get this idea. So of course we can get a whole thing. So for the web, we can work out. So I will not put integration of these things put all together. So it's a number we can work out. Just to let you know, this will flow. So from here and then downwards and then go further. So same way for the moment, we can work on the R. So and then of course we can get a whole thickness because it's small. That's the first moment of this part. T cubic could be ignored. It's from math. So you don't understand, doesn't matter. Okay, just let you know, okay? Because T is thickness, that's why the T cubic will become small. For example, if a 0.01, the cubic is very, very small. That's why here we can ignore for these parts. So that's why for here, we get a much simple way to get the two parts together. So the R we can work out. So now we can find here substitution this value into this equation. So then we can see that's we can get to the FW is a V. So that's why for this thing we can see that they put all the values put together will be equal to the shear force we used from the method of section. Okay, so that's why from here we can work out these things. So okay, doesn't matter for these things, okay? But still from here we can get R beam, how they values each other to go. So basically, when do anything here, so of course you can see it's R beam. They put R beam here, we can see the conclude for the V, because it's still like it's a method of section, we work on a V. But this time we change linearly. You can see here, this is linearly, but here is a parabolically, okay, of these things, as we mentioned from this equation. You see, this one will be different. This one is linear. This one is different. So of course, based on this one, it's always parallel to the wall of the beam. But for the direction, so you can see this one we go to inwards on the top, and we combine together as a flow and go to outwards of the sea. That's why you can see, hey, how we design these things. That's how they flow like this way. So of course, there's so many other things for the T beam. for the triangle, for U, for circle. So they have a different direction of these things. So just show you this idea. Doesn't matter for this thing, okay? Just give you idea how this thing will be work. So lastly, we still strengthen these parts. Okay, how we understand these things? Because for example, this is a box. Okay, so that's why for different location we use pins. You will see the value will be different. But still somewhere, I know you have questions for these things. Okay, somewhere one this thing, one other way. Okay, I will try to mention where's the thing, but someone should check back. For example, here a thin word box beam is subject to shear over 200 kilonewtons. So determine the variation of the shear flow throughout the cross section. You see, this one is a box of this thing. And also dimensions are shown here. You will say, hey, what is this value? Remember, I said this one only tell you we need to work out from method of section. Okay? Get the idea? Because the value given to you because they will say from method of section. So that's why we'll just straightforward tell you how this value will be. For shear flow, of course, we should know that's number of Q equal to VQ over R. Of course, the Q will be equal to Y bar times A. Remember, this one, why use a prime? Because the prime that means from here to inch of center to the outermost. Just that's the way. But the Q is a Y bar times A from -2 and also from engineering mechanics. So, of course, from here, we can work out. So, first thing, we must work out the moment of inertia of the whole cross section. Okay? So this one, of course, quite easy, rectangular one, another rectangular one, but here is square, okay? I think it's square. So that's why from here is the B 1 over 12 BH cubic. But this one is empty. That's why minus 1 over 12, this one, so 0.1 times B cubic. So that's what I should know. So this one from existing knowledge, we did so many of these things. So later on, we should work out the location BCD of this. Everyone look carefully of this thing. It's very interesting, okay? For example, I put a text here to let you know these things. Otherwise, some, oh, where's this? I put text. Only for the B, see? For the B, the point here, the area, because the only point is in the center of these things. So that's why like a point value. That's why here, the area will be roughly equal to 0. Okay? Count 0, remember from 1 point to outermost. This is only 1 point. That's no meaning of this. Because from 1 point, outermost, 0. Okay? So the almost 0, the QB will be equal to 0. That means QB will be 0. That means Q0, VQ, that means shear flow will be equal to 0. Are you clear? Okay? So now for C. C, where's the C? Look here. C is here. Clear? C is here. Also could be here. Why? Because there's a symmetry. So they should be equal to each other. So of course, I put a comment here. This is why I comment here. For point C, the area A prime is shown in the shader. Okay? Since we cut point C, so the cut section has 2 faces. Could be here, could be here. So that's from here we can see as 2 faces to support. So we only work for one part. So that's why we then divided by 2 of them. Can you understand this one? That's because over here. Same of this. This one equal to each other. So this one didn't see the pin, but because it's one structure, you will put a pin, you must put a pin together. But because it's put a circle, so that's why you can see this one will support, this one will support. So that's why from here, this one will support. This one, another point equal, because this one we didn't see the pin or screw, but actually they will support the same moment of these things. So that's why from here, they work this thing, these parts, they were equal to each other of this because of symmetry. So that's why same like two screw put together. So that's why for here we should divide by that. That's a QC, the whole thing over here, YA. So that's why here it's we can see the values, location. You should work by the location by yourself because it's half of this one times the half the locations of this. So that's why here the area is 0.015 is 0.125 times the height 0.025. So I can get this thing. Now QC should be half of flow. Okay, so half flow that will be used for the calculations for here. So VQC of I, but half because there's a two will support the same amount. So that's why here we should use a half of this thing. So that's why put the value VQ, which will work out, I will work out. That's why I can see this value. Same way for D point here. Okay, but QD will be like this way. It's this part together. So from here, we still have two parts. One here, one here. So also divided by 2. So that means from here, you say, where I didn't see. So if this one, you will say this is a box, like this way, from the beginning, okay? That's why I mentioned to you, you should know where it's come from. That's the most important. We should know where it's from. For example, here. This one is a box. Clear? You can see here the different color. Can you see? Because they will use pin or rivets or nails or something they put together. So that's why from here, you will see this one, that one will be equal to each other because they support the same location. Symmetry. For anything here, if this one half, you put the same location, they also will put one pin there. So that's why we should know the meaning of these things. This one supported the whole area by 2, not only by 1. Hopefully you can convert these things, okay? You didn't see the pin because this one is a structure. But put a pin, you will say, put a pin, you can see. But you can see, you didn't see pin here. But you can use a screw. Can you see? Can you see pin here? You cannot because there's a screw inside. Okay? So that's why from here, so we should get the idea. So that's why for here, this is our parts of 2, not only one of these things. For example, here. Here, you can put this side and put this side, but there's 2 will support together. You can only put one side. Clear? You will see for the weddings, you put one side weight, another side put another row. So that's why you cannot put only one wedding. You cannot put 2 weights. So that's why because they will support equal of these things in the same location. So look at this. This is more careful. Okay, this is more clear here. Look carefully here. This one is a box. Clear? This is support. You can see this one, when this one, CC or DD will be equal to each other. Can you see this one? Okay, this one you can see. Okay, you see this one, same location. CC or DD, you will change the location. You can see they will duplicate. Okay, so that's why from here, CCDD will be equal. So that's why there's 2 nails or 2, depends on how this thing, okay? 2 nails, 2 screws, 2 rivets, or 2 glues. They will equal support. So that's why from here, we must get this idea to work out. So that's why from here, so for this kind of parts, okay, the first thing we should realize, I haven't looked at it, I just say this is very important for you. So we work on this F is equal to QS. That depends on how many spacing of this thing. So there are how many, you see how many the nails, how many screws you should work out for these things. So for example, here is a 1, 2, 3, 4, for example over here. So that's why for here we should know the spacing. But remember, when you do anything here, we must get the idea of for the shear flow, how many we can work out. Whether it's a multiply, whether it's a divide, depending on the question. Okay, so that's why here if a multiple, if a single is easy, you can work out. But if a multiple, then we say you were lost the direction. So that's why for here we should play a little bit. Clear? We should play a little bit for these things. Okay, so that's for this part. We still have some further readings just for your interest, for yourself to get this idea. So further readings. So for here, so there's some other thing for the shear center, because if this one is not in the center, they were twist. For example, this one because of the flow, this will twist the locations. You see, like this one. Okay, that's why for here they can find some location to find the center. You see, for these things, you see, change the location. So that's because of the shear flow of these things. Okay, but this was broaden your knowledge to get the idea, not for exam, for further readings. Okay, that's all for this part. So then we use tutorial question to get some idea. Okay, thank you.